Okay, so just for the sake of the video, reminder, check the report card semester grade. Against deadline. That's just it. And then we are going to go back and take a look at page 252, number 16. And yesterday we had gotten so far as drawing for ourselves a conical pile, like so. And if I remember correctly, we had marked a diameter, and we had marked a radius, and we had marked a height, and the problem told us that the height was 3/8 of the diameter, and the problem also told us that the height was 4. Is that correct? Okay. And from that, we pretty quickly figured out that the diameter was 32/3. Let's actually mark that value here. And then we were told one more thing. We were told that sand was pouring onto the pile at a rate of 10 cubic feet per minute. These dimensions here are also in feet. And remind me again, what did we label that 10 cubic feet per minute as?
DVDT.
We marked it as DVDT, and what was the logic that led us to marking it as DVDT? The units. Very good. What about those units? Feet cubed on the top, which tells us the units of the thing that we're working with, and then per minute on the bottom. What's that? Oh, is it meters?
Oh, yeah.
Everything's in meters. Okay. All right. Everything's in meters. Poof! The pile just got 3 times as big in each direction. Okay. And so now the question that they're asking 2 questions, right? At what rate is the radius changing of the pile, and at what rate is the height changing? And we're going to answer those questions separately. Okay? Somebody translate for me into math the rate of change of the radius. How should I write that? Yep, that's it. So I'm looking for dr/dt, and what I am given is the volume dv dt. And so I need to begin with an equation that relates the volume to the radius, and I do that according to the shape of the pile, which is a cone. So I look up in my brain or in Google the volume of a cone, and what do I find? Volume of a cone is? Exactly so. So this is my formula, 1/3 for pi/3 r squared times h. Now the only thing that makes this problem be a little bit different from the previous problem that we worked is that my formula has 2 variables in it, right? And both of these variables are actually changing, so I cannot replace them with constant values. This is key. This is key. We cannot substitute before we differentiate for things that are changing, things that are not constant, because I need to include their rate of change in my computation. So instead, I'm going to need to substitute my variables away. And since I'm looking for dr/dt here, I'm going to substitute for the variable that I don't know, h. What do I know about h? I know that h is 3/8 of the diameter. And the diameter, what is the diameter in terms of the radius? 2 times the radius. So that my height is 3/4 of my radius. Good? Yep. And so that height is 3/4 of the radius, goes into my equation right here. And a little bit of good news, I see factors of 3 that cancel. So that I get pi over 4 times r cubed is the volume strictly in terms of r. What I have now is a formula for the volume of this cone knowing only the radius. And I'm ready for a derivative. So that dv dt is equal to now 3/4 pi r squared times the derivative of the inside dr dt. And now that I have differentiated, I am ready to plug in values. My dv dt is 10 meters cubed per minute. My radius, boy, I got to go back and look that up. My radius was, my diameter was 32/3 meters, so my radius was 16/3 meters, right? And now it's just a matter of solving. dr dt is equal to, how about we divide both sides by all of this? And call it a day. Sure. Notice that this problem used the same process as the previous problems that we did yesterday. The only difference was that our initial formula for volume had 2 variables in it, so that we needed another condition to substitute away. And that second condition was given to us that the diameter was always, the height was always 3/8 of the diameter. And so we worked that into an equation that we can substitute. Sure will. While we're scrolling back down, we've only answered one of the questions. The other question for us was, what is the rate of change of the height? What rate is the height change? So I'd like for you guys to now tackle that question. I'll accept for Jesse to spit out his gum. Times the derivative of the inside. Watch your variable. You're taking the derivative with respect to time and with respect to radius. So you can change the derivative with respect to time of some function of r is going to be the derivative with respect to r of any function. Time is the derivative of the inside. The inside is r itself. Yeah. Notice that you can't really abbreviate like that. Hi, welcome. We have a new student. Ken, this is everybody. Hi, Ken. Hi. You'll get to know them. For today, why don't you pull up right here? We're finishing up some related rates, which you've done already, right? Okay. And then we started on integration on so that's where you go from. Right, so Lee is asking about this notion of derivative of the inside, and where do we get this? here's one way to see it. The r is changing, right? And so that means that r is a function of time. So if I were to write this out in more formal notation, I would write it like this, that the, we have to go back here, that the volume as a function of time is pi over 4 times the radius as a function of time cubed. That's our complete thought here. So that now when I take the derivative with respect to time, and that's the key, it's a derivative with respect to time, not radius. Then using chain rule, I do outside inside, and that gives me 3/4 of pi times r of t squared, that's the outside, times r prime of t, which we spell as dr dt. Oh, yes.
I missed the step when you did r squared, so I was like, what do you do?
Ah,
Now, right?
that makes sense. Yep. Right. So we have differentiate first, then plug in. And guys, unfortunately, we cannot reverse the order of those two steps. If you try to plug in before you differentiate, then you are fixing that expression at one moment in time, and everything is now constant, and all your rates become 0. So you have to differentiate first to get a rate of change, followed by substituting your values. Yes?
Where'd you get the dr dt right there?
That's exactly what I was explaining to
so
Lydia.
I'm just, because if you're already, the 10 meters cubed per minute is already a rate, so if you, I'm just confused right there.
Okay. So you're confused about here to here, or you're confused about the differentiation process?
Yeah, that part.
Okay, right? So we are taking a derivative with respect to time,
Yeah.
not with respect to radius. So that when I take the derivative with respect to time, I have to think of r as a function of t,
Yeah.
exactly like I have here, which means I have to think outside-inside chain rule. The outside is r cubed. The inside is r.
I got that part, but for the other side.
Oh,
Where-
here. Well, I
where's
took
that
the
coming
derivative of v with respect to time. So when you take the derivative of v with respect to time, you get dv dt.
Okay, I see. I see what it is.
Good. Okay. Now you guys had to find dh dt as well, so talk me through that process. How does it go? Jesse Jung, you're on. I'm really asking for the process. Show me your work. How do you get there? There's actually two ways you could do this. And those two ways correspond to starting with the two rates that we know already. What two rates do we know already? We know dr dt and we know dv dt. And you can get to dh dt from either one of those rates.
Would you take the answer that we just got?
Yeah. Go ahead.
Oh, the equation you had at the beginning, h equals 3/4 r.
Ah, look at that. So we start with an equation that relates h to r, and then what do we do with that?
Take the derivative of both sides.
With respect to
T.
t. Go ahead.
So then dh dt equals 3/4, and then you plug in the
3/4 of,
dr dt.
yeah.
You get to plug that all in, get it out.
So we had this sort of monstrous thing, which perhaps we wanted a calculator for, but perhaps not. And so we can plug it all in, giving us 10 over 3 pi over 4 times 16 thirds 16 thirds squared. It's ugly, but it is just a number. And we could get a decimal approximation. Did anybody get a decimal approximation? None of you got a decimal approximation. You need to get out one.
You can get rid of 3/4.
Yeah, you can cross out the 3/4. In general in life, let me encourage you not to wait until somebody tells you to find a decimal approximation. Make that a habit. If you have a calculator available to you, yes. Yes, it's smart right. When you plug in the DRDT, so I didn't really get rid of the units. They're still there. Meter cubed per minute, and this would be meters squared. What do the units turn out to be? Let's pay attention to just the units here. On the top, I've got meters cubed per minute divided by meters squared. What is meters cubed per minute divided by meters squared?
Meters per minute.
It's meters per minute. Division is multiplying by the reciprocal. So, in the end, I want to express this in terms of meters per minute. Does that make sense for units of DHDT? James Perry thinks so. Why? Units of height at the top, and the per minute, we give it the units of a, as the units of time, but in general, if I have units of something divided by time, then I'm looking at a rate of change, exactly same. So what decimal approximation do we end up with here?
0.1119 meters per minute.
We'll just check this. 16 thirds divided by 3 should be about 5. So that squared would be about 25 times about 3. It's going to be about 75, a little bit larger than that. So we have 10 over, let's call it 80. 10 over 80 would be 0.125. That looks pretty good. Okay. Notice the estimating in your head process should happen as well. Everybody needs to know basic decimal fractions, such as 4.6. Okay. I said that we could solve this by going back to the radius equation. What's the other way that I could do this? Starting with my volume equation. Go ahead, give me details. Yeah, start with that volume equation. So, you mean 1/3? Yep. Okay, keep going. Not ready for that yet. Why am I not ready for that yet? Yes, I've got two variables, and I don't want to mess with the two variables. I mean, I can, but I'd rather not. so what do I do about that? And what do I sub in?
Well, you want H to, so,
H does equal 3/4 of R. And what do I get? Oh, you hit a roadblock. What's the roadblock and how you gonna fix it?
you need to do it apart,
There you go. The roadblock that she hit is that when she tried to substitute, oops, we got rid of the wrong variable, right? So she realized, oh, I need to actually solve for R here, and that gave,
for
good. Okay. Does anything else need to happen before I'm ready for a derivative? What would be a really good idea to do at this point before derivative? Let's simplify this, yeah. What do you get when you simplify it?
you, okay, well, can I, when you are distributing,
Students think of it as distributing because it kind of looks like the distributive property of multiplication, but it isn't really a distributive property. What it really is an exponent property. And the exponent property is that if I have a times b to the n power, then that is a to the n times b to the n. So why is that? Well, because a times b to the n means multiplying ab times itself n times, right? So I have ab times ab times ab, right? And now I understand that multiplication is commutative and associative, so I can multiply together all my factors of a first. How many of those do I have? And then I can multiply my n factors of b together as well. So, coming back to this is going to be what?
oh, I'm sorry, 16, not,
Yeah.
I just multiplied it by 2. And H,
Uh-huh.
I,
Yep. So clean it all up for us. Our final volume is?
I'm drawing a blank. 27. Okay, so 16 pi divided by 27.
That's it. Good. Very good. Andrew, give me a derivative with respect to time.
So you're gonna take ddt and sides.
Yep.
And you're gonna
Go ahead.
So your dvt equals, let's see. So let's see. Okay. So you pull out the constant.
Yep.
And then you have 3h squared. Or, not 3 dh.
He's making it too hard. What slogan does he want to remember? What does he want to remember? Catherine. He's making it too hard. What does he want to remember? Amanda, help him out.
What's the random disease?
Uh-oh. What is the derivative of h cubed with respect to t? Okay, so why is that? What derivative rule are we using?
Chain
We're using the chain rule. What's our slogan for chain rule? Right, outside, inside. Yes, you're making it too hard by trying to do it all at once. Outside first.
Outside through it's gonna be
It's going to be 3.
three. No, but
The outside is the derivative with respect to h.
okay, right. So you just DHDT. That's
The
it.
outside is the derivative of this expression with respect to h.
Okay. So then it's just 3h or 3h squared.
Just 3h squared. The inside is the derivative of h with respect to t, which is dh dt. This process is not hard, but it escapes a lot of students because they want to make it complicated. Outside, inside, done. And Leibniz comes to the rescue here. If I have a function of h, which I do, right, then df dt equals df dh times dh dt. The derivative of f with respect to h times dh dt. This was the logic that we used with implicit differentiation, right? We took the derivative of, say, y squared with respect to x, and we got 2y dy dx. Why? Because it's the derivative with respect to y times dy dx. This is a crucial point, so if anybody is fuzzy on this at this point, now is a really good time to stick up your hand and say, explain.
So is df dh equal to 3h squared? And that's
Yes, exactly. The derivative of this with respect to h.
And then the dh dt is what's afterwards.
Is what it is, that's right. Okay. So no further questions on that. All right, and so now we would need to, in order to evaluate this, we would do the same thing that we did before. I kind of like canceling my factors of 3 here. And now I need a value for h, which I believe I already had 4, right? Check and make sure that was correct. H was 4. So that yep. Okay, now of these two, which was easier to accomplish? Definitely the first one here. But in order to make this happen, I had to have some situational awareness. I needed to recognize that I already had a value for dr dt, and I could then relate h to r. So how do I have that awareness? What do I look for? It's actually pretty simple. It goes back to the labeling process that we have right here. The labeling of this rate as ddt was crucial to getting the problem rolling, because I was then able to say to myself, I have a rate of change of volume. I am looking for a rate of change of radius. So what I need is an equation for volume and radius. If you're stubborn about that point, your labeling can help you make an easy decision. I need an equation that relates volume and radius because I have dVdt and I'm looking for drdt. Once I had drdt, and I'm trying to solve the second part of this, dHdt, I can now say, okay, what rates do I have? I have dVdt, I have drdt. Is it easier for me to find an equation that relates radius to height or volume to height? And the answer is pretty clear. It was radius to height because I already had that equation. That's the thought process that you want to engage in as you solve these related rate problems. Okay, let's take a look at one more problem here. I want you all to consider problem number 23. And in problem number 23, we have a curve y equals f of x equals, is it 10 over or 1 over 10 plus? It's 10 over 1 plus x squared. Immediately sketch this curve here so we know what we're talking about. Go. Your sketch should look something like this. How did I know?
I got that, and then I got an error.
What did your error say?
It says I tried to.
That it didn't go to. Syntax means that you spelled something wrong. What did you spell wrong?
Oh, okay, sure, yeah. Negative sign.
Syntax error is just a spelling problem. How did I know that the graph of this looks like so? How did I know the curve looked like this? I did it with just 2 easy steps. What are the things that we do? You hold poles and zeros? F prime would be probably hard. I probably didn't do that in my head. Right? Limits, absolutely. If I take the limits out at infinity, what do I find? What does that find for me? Horizontal asymptotes, absolutely. And that's easy to do. What's the limit as x goes to infinity of this expression?
0.
0. And as x goes to negative infinity as well. So that gives me horizontal asymptotes. And from there, it was kind of easy to find what's the easiest point to find on this curve? The point when x equals 0, right? And so if I just find the point 0, 10, and I find the horizontal asymptotes y equals 0 right here, now I can draw a curve that fits that description, and it has to look like this. Everybody see that? So you want to have these curve sketching kinds of things in mind. You should be able to do these sorts of things in the wild. You know how to use all these tools. Now it's just a matter of saying to yourself, oh, I can do it. So I sketch this curve. And what we're told now is that a particle is moving along this curve so that dx dt is equal to 3 centimeters per second. So the picture that we have is we have maybe a small insect or something like this. And the small insect is moving along so that it maintains constant horizontal forward progress. dx dt equals 3 centimeters per second. And they ask us now to find dy dt at 3 different points. When x is equal to -2, when x is equal to 0, and when x is equal to 20. Just like this. Now, what I notice here is that I'm trying to relate the rates of what two quantities? X and y. So thinking through my process, I need a relationship between x and y. Yes, I have a relationship between x and y. And that relationship is what? Exactly so. So the only thing that's lacking now is a derivative with respect to time. Go. Everybody find that relationship. Matthew, you're on. It's all right. Go ahead.
No, I don't even know again. I didn't do that a lot.
Sorry. Engage. I need a derivative with respect to time of this expression.
Wait, what am I doing?
Some people do best talking out loud. Some people do best writing stuff down first. How many are in the category of writing stuff down first? How many are best at just talking? People. I'm more of a talk it through kind of person.
yeah. Okay,
Alright, go.
negative 20x over x to the fourth plus 2m squared. I didn't really I'm really sure that worked.
Huh. Tell us what process you did engage in to get that.
I have to like that.
Oh, true, it's not
I did that.
Quotient. All right. What's he missing, guys? dx dt. Yep. And now with this expression, I can plug in x equals -2, x equals 0, and x equals 20 easily, and get values for your. Yeah, it's kind of right. So you're outside.
Not this one.
That's it.
Clouds. Gray clouds.
Press OK.
We have a value for dx dt already.
Wait, I should have shared it.
So that value
No.
is in the.
What is that?
You're like an bothering me.